welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be looking at the topic the mole, and we're going to be looking at back titration. So previously we have been looking at other types of titration. So today we are going to look at how back titration is calculated, and then we'll do some practice questions. So a back titration is a titration method where the concentration of an analyte is determined by reacting a known amount of excess reagent. So the remaining excess reagent is then titrated with another different reagent to find how much of the excess reagent remained after the first reaction. So the original analyte concentration can then be calculated. In a regular titration, the original sample is titrated. In a back titration, a known amount of reagent is added to a solution, then allowed to react, and the excess is titrated. Back titration may be thought as a normal titration, but it is done in reverse. So it is also referred to as indirect titration. So when you look at this image, we can see, for example, there is an excess amount of reagent A. So this is the excess amount of reagent A. So some part of the reagent A are used to react with reagent B, and then the excess part is used to react with reagent C. So what happens is we always start with a known. We start with calculating the amount that reacted with the known value of reagent C, and then we subtract from the original to get what was used for the unknown amount. We are going to look at the questions and see how it's done. So the analyte is permitted to react with an excess reagent, and then a titration is conducted on the remaining quantity of the known solution. That way, this is a way to measure the amount that remained unreacted. That is excess quantity. So let's look at an example so that you can be able to relate what we have seen. So when 4 grams of metal carbonate was dissolved in 160 centimeters cubed of 1 molar hydrochloric acid, and then the resultant solution diluted to 1 liter, 25 centimeters cubed of this solution required 20 centimeters cubed of 0.1 m sodium hydroxide solution for complete neutralization. So first of all, if we look at the diagrammatic representation, first of all, we have a beaker that's containing 160 centimeters cubed of the HCl that is reacted with 4 grams of metal carbonate. So this reaction undergoes and goes and goes, and then we only pick a small amount. So this one is diluted to 1 liter before we pick a small amount. So at the end of the day, now we have 1 liter of solution. So we added the water. So remember, nothing really changes here. So some of the hydrochloric acid will react with the carbonate, and then we only pick 25 centimeters cubed of this solution. This 25 centimeters cubed is what we add the 20 centimeters cubed of the sodium hydroxide. So we are just going to go back. We'll look at how much of the acid reacted with sodium hydroxide in the 25 centimeters cubed. We get the moles of the acid, but now we are going to go back and equate those moles to the ones that are in the 1 liter. So we get the amount that reacted with the carbonate. Basically, we are just going back instead of going forward. So we will start with the sodium hydroxide, like from what we know. So your first question is to calculate the number of moles per liter of excess hydrochloric acid that reacted with sodium hydroxide. So we can write the equation, which is sodium hydroxide aqueous plus hydrochloric acid aqueous to form sodium chloride aqueous and water. So this equation is balanced, so the mole ratio is to 1 is to 1 is to 1 is to 1. So we have already been given some information on the sodium hydroxide. We have been given the molarity, which is 0.1 molar, which means is 0.1 moles in 1000 centimeters cubed. So if you want to calculate the one that was used in the reaction, so what about in 20 centimeters cubed? So it's going to be 0.1 times 20 divided by 1000, which gives us 0.002 moles. So these are the moles of sodium hydroxide that reacted with hydrochloric acid. So if you look at the mole ratio of sodium hydroxide to HCl, you'll notice that the excess acid that was used, the number of moles is also 0.02 moles. So the moles of acid that reacted with the sodium hydroxide are 0.002 moles. The next question is calculate the number of moles per liter of acid that reacted with the carbonate. So basically the concentration of the acid that reacted with the carbonate. So now we have the moles of the acid that reacted with the sodium hydroxide solution. But remember, this was the one that was in the 25 centimeters cubed. We need to get the moles that are in the 1 liter. So we will say if 0.002 moles of hydrochloric acid were in 25 centimeters cubed that reacted with the base, what about the ones that were in the 1000 centimeters cubed, the one that you were dissolving the M carbonate? So it's going to be 0.002 times 1000 divided by 25, which gives us 0.08 moles. So these are the moles that were in the 1 liter. So that is the question that you have been asked. So these are the moles. Basically, these are the moles of the excess acid, but now in the 1 liter. But now remember, we want to get the moles that reacted with the carbonate. So we'll take the original moles of the acid, we subtract the excess moles of the acid, so that we can get the ones that reacted with the carbonate. So the original moles, you have already been given the molarity of the acid, which was 1 molar. And now we subtract the ones that reacted, which was 0.08 moles. So we'll get moles, this is moles per liter or molar. So let's correct that. So the original moles of hydrochloric acid cannot be 1 mole because we said we dissolved 1 mole hydrochloric acid in 160 centimeters cubed, then topped up to 1 liter. So let's get the original moles. So we know 1 molar means is 1 mole in 1000 centimeters cubed. So what about in the 160 centimeters cubed? Remember, 160 centimeters cubed is what we have. So it's 1 times 160 divided by 1000, which gives us 0.16 moles. So these are the original moles of HCl before the reaction occurred. So when we subtract, it's going to be 0.16 minus 0.08, which will give us the moles that now reacted with the carbonate will be 0.08 moles. So these are the moles of HCl that reacted with the carbonate. So I hope you have understood what we have done. So we calculated the original moles. The original moles were 1 molar of hydrochloric acid dissolved in 160. So it means 1 mole was in 100, but we only used 160. So we get the actual moles, which was 0.16. But the ones that were excess that went to react with sodium hydroxide was 0.08 moles that we had calculated before. So we subtract the original from the excess, so we get the actual that reacted with the carbonate. So the number of moles of carbonate that reacted with the acid. Now we have the moles of the acid that reacted with the carbonate. So we write the equation. So it is M carbonate plus hydrochloric acid to form chloride plus carbon 4 oxide plus water. So we put a 2 here. So you will notice the reason why we gave M the valency of 2 is from the formula of M carbonate. You see carbonate has a valency of 2, so if it combines with M and the valencies cancel, it means the valency of M is 2. So the mole ratio is going to be 1:2. We already have the moles of the acid, which is 0.08. So the moles of the carbonate is going to be 0.08 divided by 2, which gives us 0.04. These are the moles of the carbonate now that reacted with the acid. And then we go to the next question, the formula mass of the carbonate. So we go back to the question, you are given the mass of the carbonate as 4 grams. So we have the mass, which is 4 grams. We also have the moles now, which is 0.04 moles. So we can get the molecular mass, which is the same as, when you look at moles is equals to mass over molecular mass. This is the same as molecular mass is equals to mass over moles. So our mass is 4 grams over 0.04, which will give us 100. So the atomic mass of M, so we have M carbonate. If you had the atomic masses of each, you're going to get 100. So M we don't have, but we have carbon, which is 12. We have oxygen, which is 16 times 3, because there are 3 is equals to 100. So this is 48 plus 12, which gives us 60. So M is equals to plus 60 is equals to 100. So M is equals to 100 minus 60, which is M, the atomic number is 40. So I hope you have seen how we have calculated that. Let's do another question. So 0.6 grams of potassium carbonate. So potassium carbonate has that molarity or concentrations grams per mole is dissolved in enough water to make 200 ml of solution A. 20 centimeters cubed or 20 ml alloquent of solution A is taken and put in an ml flask. To the flask is added 20 ml of 0.17 hydrochloric acid. The resulted solution is then titrated with 0.140 molar sodium hydroxide. How many moles of sodium hydroxide were used? So first we are reacting the potassium carbonate with hydrochloric acid, and then whatever excess hydrochloric acid that is remaining is reacted with sodium hydroxide solution. So the first thing that we are going to do, we are going to use the potassium carbonate to write the equation. We react it with hydrochloric acid to give us potassium chloride plus carbon dioxide plus water. So we balance this equation by putting a 2 here, which causes us to put a 2 here. So that balances the equation. So the mole ratio of the carbonate to the acid is 1:2. So when you look at the carbonate, we have been given the grams per mole, which is 138.2055 grams per mole. That is the concentration. And then we also been given the mass, which is 0.6. So if you want to get the molarity in moles per liter, or we say moles per liter, you look at the mass per liter, which is 138.255. You divide by the mass. So the molar mass of potassium carbonate is going to be 39 times 2 plus 12 plus 16 times 3, which is going to give us 138.2055 divided by 138, which will give us. So let's make a small correction. So the value that we were calculating was already the molar mass. So we have the mass, which is 0.6 divided by the molar mass, which is that 138.2055, which will give us the moles will be 0.0157 moles. So remember, these moles are being placed in the 200 centimeters cubed solution. So if 0.0157 moles are in the 200 centimeters cubed. What about 20? Because only 20 was taken to react with the acid. So what about 20 centimeters cubed of the solution? So it's going to be 0.0157 times 20 divided by 200, which gives us the moles that were in the 20 ml was 0.00157 moles. So those are the moles that were in the 20 centimeters cubed or 20 ml that reacted with the acid. So if we look at the reaction, we know that the mole ratio is 1:2. So we can get the moles of the acid that took part in the reaction. So you're going to use the mole ratio, which is 0.00157:2. So let's put that down, 1:2. So 0.00157. So for the 2, it's going to be 0.00157 times 2, which gives us 0.00314 moles. So these are the moles of the acid that reacted with the carbonate. So next we are going to look at the moles of the original moles of the acid. So original. So initially we had 20 ml of the 0.01700 molarity of HCl. So let's count the number of moles that were in this 20 ml because that is what was in the volume, but only 0.0314 moles reacted with the carbonate. So the rest is what reacted with sodium hydroxide. So 0.17 moles are in 1,000 centimeters cubed. What about in 20 centimeters cubed? So 0.17 times 20 divided by 1,000 gives us 0.0034 moles. So these were the original moles, but the ones that reacted with the carbonate was 0.0314. So we will say original minus the excess, or the ones that reacted with the carbonate. So it's going to be 0.0034 minus 0.00314, which gives us 0.00026 moles. So these are the moles of HCl that reacted with sodium hydroxide. So we know the reaction between HCl and sodium hydroxide is going to be a ratio of 1:1. So if the moles of the acid were 0.00026, it means also sodium hydroxide was 0.00026. So the question is, the resulting solution is titrated with this molarity. How many moles, or how much volume of sodium hydroxide was used? So we are going to use the molarity, which tells us if 0.1048 moles are in 1,000 centimeters cubed, how many mole volume will contain 0.00026, will have how much volume? So it is 0.00026 times 1,000 divided by 0.1048, which gives us 2.48 ml. So that's how you are able to calculate. You notice this is a bit unique question than what we have been discussing. So first we look at the one that reacted with the carbonate, and that tells us, if we subtract from the original amount of HCl, that tells us what reacted with the acid. So next, you're going to look at the final question for practice. So you have been given 0.9030 grams of M hydroxide was mixed with 20 ml of 2 molar hydrochloric acid, and enough water was added to make 100 ml of solution A. Then a 10 ml of the alloquent solution A was taken and titrated with 17.464 ml of 0.05121 molar of sodium hydroxide. What is metal M? So first you look at the reaction between sodium hydroxide and HCl. So it forms sodium chloride plus water. So the mole ratio is going to be 1:1:1:1. So let's look at the moles of the sodium hydroxide in the solution. So 0.05121 moles are in 1000, but the ones that were used in the reaction was 17.64 centimeters cubed. So this gives us 0.05121 times 17.64 divided by 1000. These moles of sodium hydroxide that were used are 0.000903 moles. And since the mole ratio is 1:1, it means the moles of hydrofluoric acid that took part in the reaction was 0.000903 moles. Next, we look at the original moles. Remember, these moles are in the 10 ml or 10 centimeters cubed. So we go back. So if 0.000903 moles were in 10 centimeters cubed, so what about the one that were in 100 centimeters cubed? Because that's where we removed the sample of 10. So it becomes 0.000903 times 100 divided by 10, which gives us 0.00903 moles. So these are the ones that were in the 100 ml. So let's look at the original moles of HCl. So we are told the HCl that was mixed was 20 ml in 2 molar HCl. So 2 molar, it means there are 2 moles in 1000 centimeters cubed. So what about in 20 centimeters cubed? We crisscross. This gives us 2 times 20 divided by 1000, which becomes 0.04 moles. So these are the original moles of the acid. So the ones that reacted with the sodium hydroxide are 0.0903. So we do the subtraction. So 0.04 minus 0.00903, which gives us 0.03097 moles. So these are the ones that reacted with the heme hydroxide. So let's look at the equation for the heme hydroxide. So heme hydroxide reacts with hydrochloric acid to form M chloride, and it's going to be 2 because you can see the valency of M is 2 plus water. So we put a 2 here and a 2 here, and our equation is balanced. So the mole ratio is 1:2. So we already have the moles of the acid, which is 0.03097. So the moles of the hydroxide will be, you divide this by 2, you get 0.01548 moles. So the next question, you have been told to calculate what is metal M. So we have the mass. So the mass is 0.9030, and then we have the moles, which is 0.01548. So molecular mass will be mass over moles, which is the same as 0.9030 divided by 0.01548, which gives us a molecular mass of 58.3. So if we look at the heme hydroxide, it was written heme hydroxide, which the totals to 58. So M plus 16 times 2 plus 2 is equals to 58. This gives us that m plus 32 plus 2 is equals to 58. So m is equals to 58 minus 34, which gives us m is 24, which tells us it's magnesium. So that brings us to the end. So I hope you have been able to follow through. You can go through the video again slowly by slowly, look at each step so that you can be able to see how we did the question. So see you in the next lesson.